Good morning. Today we'll be renewing the thermal design aspect of electronic equipment using convection heat transfer, and the specific topic of interest today is natural convection in electronic packaging. While force convective discussions we carried out in the last few modules, and this one is specific to natural convection, which is often referred as free convection as well in the systems. So, the goal is to understand where this happens. So, modern day electronic devices like smartphones and tablets often restricted, or their design evolution or high power performance is restricted by thermal design and power delivery. And thermal design is such that for smartphones, since we hold the phone and talk to a person, the skin of the phone should not exceed a certain temperature. So that, for example, is roughly approximately about 41 to 45 degrees Celsius, depends on the manufacturer and stuff. So the skin temperature imposes a maximum temperature the skin can be allowed, and the processor which is inside the phone has to dissipate, and the processor temperatures, as we discussed in the past, is maybe on the order of 90 to 100 degrees Celsius junction temperature. So the overall temperature difference that can be supported by this system is about 90 degrees Celsius or so, minus this 41 or 45 degrees Celsius. That is the temperature driving force that can be supported by these phones. Once the skin temperature exceeds that 41 or 45, which becomes ergonomically uneasy to hold the phone, then the processors are typically slowed down, and these phones do not carry any fans. Phones or even tablets for that matter. Most of the tablets, some tablets, the so-called the tablets that can be converted as laptops, they do carry fans with them, but most of the tablets and the smartphone markets, there is no fan in them. So the only way of dissipating heat is by natural convection, and whenever we talk about natural convection, radiation becomes important as well, because the natural convection has lower heat loss, heat carrying capacities, that radiation contribution cannot be ignored. For example, in smartphones, many analysis that people have carried out during the design shows that almost 40 to 50% of heat loss from a phone actually turns out to be from radiation in many situations. So when you are designing these smartphones, thermal design for these smartphones, then one has to understand the natural convection and also understand the radiation characteristics. So that is why some smartphones with the same model number but with different colors have different prices, because that may enable certain emissivities and certain characteristics of that phone specific to it. So with that introduction, we move to the next situation, which is how is this handled. In a typical PCBs, there are many PCBs where there are many cards or PCBs stacked parallelly as shown in this slide, and depending on, as we discussed, similar to the force convection situation, there may not exist any symmetry, or there may not exist any specific boundary condition, like should we treat that as isothermal board, isoflux board, so on. And also when it is all natural convection driven, it could even be in the turbulent regime of free convective flows, when the Rayleigh number, which is the governing non-dimensional number, if it exceeds anywhere about 10 power 8, 10 power 9, often we have to account for the turbulent characteristics. So moving on further, so looking at the next slide, is that there are two forms or two limits limiting behavior in a PCB type situation, where when you have two parallel plates in this case that is mimicking a PCB, and there is induction of flow from the bottom, and the flow due to natural convection rises up due to density difference, as you may have heard from the previous modules. As the flow rises up initially very close to the inlet, that is at the bottom shown here, that one can think of it as an isolated plate limit, that is the boundary layers are not even interacting. So, most of the core of the flow is fairly isothermal, as you can see from the profile that is shown here, that initially the boundary layer effect is seen only closer to the walls on both sides, and most of the flow is fairly flat in the internal section of the flow. As the flow rises, the interaction of these two boundary layers start to emerge, and as you can see, beyond a certain height, then they become what is called a fully developed flow limit. So, you could envision a fully development of flow even in natural convection, and so depending on that, we need to pick a correlation that works for these type of situations. The flat plate correlation, the vertical flat plate correlations or solutions, analytical solutions, are valid only at the isolated plate limit, which is closer to the inlet. So, depending on the height of your PCB, many of these variety of regions can exist in your system. So, to quickly recap, I will not go into the details here, as these things would have been covered in the previous modules. So, if you look at a flat plate and the plate is the height of the plate is against the gravity vector direction, as the flow induces into that because of temperature density difference closer to the wall, as the plate is at a hotter temperature, while suddenly you bring a hot plate into a quiescent cold temperature, that there is a near to the plate there is a density difference, because the near to the plate the air, if we are talking about air as a cooling medium, then air gets hot, and because of the higher temperature the density difference starts to occur. So, the hot air starts to rise because of the emerging density difference, and depending on the Prandtl number of the fluid, if we stick to the Prandtl numbers that are greater than or equal to 1, then you see a profile as shown in this figure, which is such that the thermal boundary layer is developing and is closer to the wall, and the boundary layer, that is velocity boundary layer, is farther away, and it is shown as in the dashed line here. So, one interesting aspect of this is that you could do what is called order of magnitude analysis to figure out what is the estimated Nusselt number. You can estimate the boundary layer thickness and so on using an order of magnitude analysis, but that is not the goal of this module, but instead to just refresh what was taught in the previous module, so that we can take some key takeaways from here, so we can apply it to thermal design. So, one important aspect that you can see from this figure is that the temperature difference is the driving force. So, the temperature difference drives a certain maximum velocity within the thermal boundary layer, and because of this emergence of this so called wall jet, that maximum velocity entrains little bit more fluid that is outside of the thermal boundary layer, and that is why you see a downward profile. So, the maximum velocity within the boundary layer is within the thermal boundary layer somewhere there, and this maximum velocity entrains more fluid in a Prandtl number greater than 1 case, more fluid, and entrains more fluid as it rises up. And so, this is a typical boundary layer in a Prandtl number greater than 1 situation, where the thermal boundary layer is within the temperature boundary layer is here, while the velocity profile looks like this, and because the peak is happening here, this fluid which was quiescent is carried more and more by this maximum velocity because of the shearing action of this higher velocity fluid to the quiet fluid that is sitting next to it. As that shear eventually dies down, you go to a zero velocity as you rises. So this velocity profile will keep expanding as long as the plate length is increasing. So that is the key to this. And if you look at the boundary layer equation for this, that the gravity or the buoyancy term shows up in the momentum equation, it does not show up in the energy equation. So that I am sure you are well aware of by now. So in this case the gravity direction is pointing in the x direction. So that is why the momentum, the buoyancy term shows up here. So if you do an order of magnitude analysis and using the boundary layer thicknesses, then one finally gets to a Reynolds number based on, for Prandtl number much greater than 1, one gets a order of magnitude analysis gives us Rayleigh raised to the power 1/4, that is 0.25. And if the Prandtl number is much less than 1, which is the liquid metal flow type situation, and you are looking at natural convection in liquid metal flows, then the interesting aspect is that it has the same power as 0.25, but the Rayleigh number is being multiplied by Prandtl number. So you have Rayleigh, which is nothing but Grashof number times Prandtl number, but you indeed see that it becomes like a Rayleigh times Prandtl raised to the power 0.25. So more exact analysis give you the same type of a behavior, and so that confirms that the order of magnitude analysis is a good way to understand or estimate Nusselt numbers. So moving on from here is that now we just looked at basics of quick review of natural convection from a flat vertical plate. Now if we stack n number of those plates and they are supposed to mimic a PCB, then as a simplest approximation we will assume that the spacing between the plates to be d, and the entire width of the PCB module is about length L, and the width is W, and the plates are isothermal. We assume that these green parts are isothermal at some temperature T naught, that is the maximum temperature you can assume while trying to design. You can assume that that is the maximum temperature that the board can reach. So with that, and assume that surfaces are smooth, which is not such a great assumption, but it is a good assumption to begin with. And so we can figure out how many number of boards by just taking L by L divided by D, because we are assuming negligible plate thickness, or the green boards are assumed to be of thickness T is negligible, so that we do not have to worry about them. As we discussed in the force convective analysis, we do the same thing. We look at it for natural convection, we look at it from two different perspectives. When the spacing between the plates are 0, that is one limit, and the spacing between the plates are infinite. So when you talk about the spacing between the plates being infinite, then the natural assumption is that it is like acting like an isolated plate limit. The boundary layer is growing on both sides of the plate, but those boundary layers are not interacting. So you can work with a typical vertical flat plate correlation to capture the impact of it. When you are talking about D tending to 0, which is the spacing between the plates being equal to 0, then we are assuming that we are in a regime where fully developed natural convection flow happens quickly, and so most of the entire height over which the flow is happening is assumed to be fully developed. So first looking at the fully developed flow, we know from our Poiseuille parallel plate analysis that you can take, if you look at this equation, rho times beta Cp. So all this is talking about is essentially the total heat transfer rate from the two parallel plates. And how do we arrive at this expression? It is purely talking about mCp delta T. When you have a fully developed flow, then one can assume that the temperature differences are quite the temperature difference, the non-dimensional part of the temperature difference is quite fixed. So, using that assumption, then one can write that if the plate temperature is T naught and T infinity is the temperature difference of the temperature of the incoming fluid, then the temperature driving force is given by this. Using this, you can write Q, you can express for a single plate, single channel, you can write as mCp using the energy balance m dot Cp delta T, and the m dot, the velocity is determined by assuming a parallel plate fully developed flow type situation, and the velocity will be a function of the buoyancy velocity. It is not the velocity that one determines in forced convection, but in natural convection there is a equivalent velocity, and that is what is being used here. And if you are talking about total heat dissipated, then you have to multiply this with the number of channels. So, that is given by L by D. So, if you look at the total heat transfer rate from these two plates, it is proportional to d cube, d square, and the q total is proportional to d square. So, similarly, if you look at d tending to infinity case, that is the spacing between the two plates are so far apart that one can use the vertical flat plate correlation, then one can write similar to what we discussed just now, that using the correlation for air, heat transfer coefficient times HA delta T is what is written here, and delta T again is the temperature driving force between the isothermal temperature of the plate and the inlet temperature. So, heat transfer coefficient is given by the vertical flat plate correlation. Here, if you calculate total heat transfer from this stack, then it is inversely proportional to D. So, you have two asymptotic limits, one is D tending to 0 limit, which gives us a D square dependence, and D tending to infinity limit, that is giving us 1 by D, that is 1 over D type of a behavior, and somewhere between the two is where the optimal spacing, that is where we can keep the optimal spacing D optima is obtained by where the intersection of these two curves happens. And that is one way to design how to place these PCBs in a natural convection environment. So, that is the goal of this. And then we quickly move to another form, which is the mixed convection, where you may have some flow, there is a fan flow, forced convection flow, and the flow could be aiding the natural convection or it could be opposing the natural convection. So, depending on the situation, then one has to account for the Nusselt number. So, typically often what is quoted in books is that Grashof divided by Reynolds number square. If it is much less than 1, then one says that forced convective regime dominates. If Grashof number divided by Reynolds number square is much greater than 1, then it is in the free convection regime, and if it is on the order of 1, then both should be accounted for. If you look at this Grashof divided by Reynolds square, the real reason why we do this scaling is that typically the boundary layer, it is based on boundary layer thickness. It is not based on some non-dimensional parameter. It is the boundary layer thickness. What, for example, let us consider Grashof divided by Reynolds square being less than 1. That means what we are saying is that if you look at a vertical flat plate as an example, and there is forced convective flow past the flat plate, then we know from Blasius solution that the boundary layer thickness is scales by Reynolds number raised to the power 0.5, and for the case of natural convection, it scales by Rayleigh raised to the power 0.25. So, the boundary layer thickness. So, what this does to us is that we need to account if the boundary layer thickness of natural convection is much smaller, then the heat transfer coefficient for the natural convection is higher. If the boundary layer thickness of forced convection is smaller, then the heat transfer coefficient from forced convection is much higher. So that means that's how we can determine whether it is dominated by forced convection or dominated by natural convection. So in order to bring two terms together, we scale it in such a way that Grashof divided by Reynolds square. So that's beyond the scope of these modules, but we can show that this essentially this ratio is only talking about ratio of boundary layer thickness of natural convection divided by boundary layer thickness of forced convection. With that, we can move on, and there are many correlations to capture the mixed convection, and one of the most commonly used one is the Churchin and Usagi's one, and we will not discuss that anymore, but it is widely available in many textbooks. And if it is a natural convection in an enclosure, there are many different regimes and different characteristics, and also that is also beyond the scope of this module. So, we will just say that one has to understand the scope of natural convection in enclosures as well as in parallel plate plates in some situations. So, what we will cover today, the other additional topic is the so called chimney effect. In many cases, for example, the so called all-in-one PCs and stuff where there is no fan mounting, they try to make use of what is called a chimney effect. What is a chimney effect? Is as shown here in this picture that was obtained from Wikipedia, is when you have a stack, a natural draft is established. So, as the hot air rises and you provide much more longer draft on top of this heated zone, then one sees that the velocities are getting accelerated as it rises through this chimney stack. So, the effect of chimney, which is essentially providing a long draft on top of where the heat generation happens, is that the effect of chimney increases the velocity, the natural convective velocities much better than without the chimney. So, the chimneys indeed in a way enhance heat transfer by increasing the velocity, but not necessarily increasing heat transfer rate. By increasing the velocity within the natural convective zone, that it improves the heat transfer indirectly. For example, let us look at this situation. We will not go into the details. This is a paper from Fisher et al. And it is published back in 1997. You have a set of parallel plate heat sink. On top of it, you have some sort of a chimney that is placed. And the idea is, can we improve, because we know that chimneys increase the velocities. So, can we use the velocities in prudently so that the overall heat transfer from the parallel plates is improved for the given same temperature driving forces. If the temperature between the plate and the inlet is same, if the temperature difference is same, then can we increase the heat transfer by placing a chimney on it, and what should be the spacing between the plates that should be accounted for. So, the way we look into it is that when you place a chimney, there is fluid induction at the bottom as shown here from 0 to 1, and from 1 to 2 there is viscous flow, there is viscous flow happening between the parallel plates through the fins, and then in the chimney there is no heat addition, and chimneys are much larger. So, most of the core of the flow can be treated by purely a Bernoulli type inviscid flow, and that is the inviscid flow chimney flow, and after 3 it goes back, the exhaust goes back to the ambient, that is quiescent. So, one can look at it from this perspective, and if we want simplified treatment, use parallel plate fully developed flow, and you can write governing equations and make some approximations, and overall heat transfer can be calculated much easily. After all these things, writing all these equations, one finds that there exists an optimal plate geometry or the spacing between the fins that minimizes the frictional losses and also maximizes heat transfer coefficient. So, one improves heat transfer by putting a chimney on top of it. Yes, this is only discussed here as an example way how to improve natural convection, because enhancing natural convection is very difficult. Chimney is one of the very elegant ways of improving natural convection, and that is why I just wanted to give you some heads up on how to improve natural convection. Otherwise, increasing surface area in natural convection always has a countering problem of increased frictional losses that reduces velocities. So just like that, we cannot increase the surface area, so one has to increase the velocity, and that is always obtained by using chimney type situations. That's example of a chimney enhanced natural convection in heat sinks.